Well, day 11 is about to begin. So far, so good this year, huh? Problems have been interesting. Let's see where we land today. As you finally start making your way upriver, you realize your pack is much lighter. One items goes flying overhead. Monkeys are playing keep away. Get your stuff back. You need to be able to predict where the monkeys will throw your items. After careful observation, you realize monkeys operate based on how worried you are about each item. Take some notes on the items and each monkey. Okay. So this is a set of input, presumably. Okay. Starting items 79 and 98. Operation new is old times 19. Test divisible by 23. If true, throw to monkey 2. If false, throw to monkey 3. Monkey 1. Starting items blah 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 blah. Each monkey has several attributes. Starting items lists your worry level for each item the monkey is currently holding. Operation shows your worry level change as that monkey inspects an item. An operation like new equals old times 5 means your worry level after the monkey inspected the item is 5 times whatever your worry level was before inspection. Okay. Test shows how the monkey uses your worry level to decide where to throw the item next. After each monkey inspects an item, but before it tests your worry level, your relief that the monkey's inspection didn't damage the item causes your worry level to be divided by 3 and rounded down. Monkeys take turns inspecting and throwing items. On a single monkey's turn, it inspects and throws all the items it is holding one at a time and in the order listed. Monkey 0 goes first and monkey 1 on until each monkey has had one turn. The process of each monkey taking a single turn is called a round. When a monkey throws an item to another monkey, the item goes to the end of the list. A monkey that starts a round with no items could end up inspecting and throwing many items by the time its turn comes around. If a monkey is holding no items at the start of its turn ends. Okay, monkey 0, monkey inspects with 79. Multiplied by 19, 1501. Monkey gets bored with the item, worry level is divided by 3. Current worry level is not divisible by 23. Item with worry level 500 is thrown to monkey 3. Okay, 98 multiplied by 19 divided by 3. Okay, I understand all that. After round 1, the monkeys are holding items with these worry levels. Monkeys 2 and 3 aren't holding any items at the end of the round. They both inspected items starting the round and threw them all. The process continues for a few more rounds. Chasing all the monkeys at once is impossible. You're going to have to focus on the 2 most active monkeys if you want the hope of getting your stuff back. Count the total number of times each monkey inspects items over 20 rounds. For example, the 2 most active monkeys inspected items 101 and 105 times. Multiply these together. 10605, figuring out which monkeys chase by counting how many items they inspected for 20 rounds. Okay. All right. So what that means is let's split input off. Come on. What the heck's going on here? Come on, input. Okay. Let's put input right there, right? We're going to need a monkey class. And it's going to have a list of long, which is items, right? It's going to have a func of long to long, which is an operation. And then it's going to have public, let's see. So it needs to have a test. Right, so we have a func of long to bool. Oh no, we just need the long divisible, because they're all divisible, right? Divisible test, public, int, true monkey, and the false monkey. Okay, so the constructor is going to be the operation, func of long to long operation, and the divisible test, and then the true monkey, the false monkey. All right, and then yeah, that's right, false monkey. I guess we can put the items up front, it's fine. List of long items. All right, so then we'll do items as items, operation is operation, divisible test is the divisible test. Sure. Test, right? And then the true monkey is the true monkey, and the false monkey is the false monkey. Okay. So as we're going through this, we're going to do index is 0 while index is less than data length, right? So they go in order here. Do they go in order here? Let's see. 0, 1, 2, 3, 4, 5, 6, 7. They go in order here. So we don't actually care about parsing that part. All right, so items text is going to be data index plus 1. You are, let's see, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 on, right? And then we're going to do split. That's fine. Long, let's see, int parse to list. All right, you just want me to pass int parse? Why not? Okay, so items, that's actually just going to be the items. It's not items text anymore because that should be a list of int. All right, and so old times old. Well, that's interesting. Yeah, so the operation is not quite as simple as I thought it was. Func of long to long. I guess if we interpreted it, we can make it ourselves, right? Let's go look at our puzzle input again. Multiply, multiply, plus, plus, multiply, plus, and then we can have old, and then we can have a number. Okay? All right. So operation is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 23. Op text is data index plus 2, 23 on. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 21. So 21. Divisible is, let's see, long parse data index plus 3, 21 on. And then true is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 29. So true monkey is int parse data index plus 4, 29. False monkey is int parse data index plus 5, 30 on. Let's do this real quick. Console write line. Let's see. We're going to say items is string join items select. We're going to need to join this with a comma, right? And then we're going to do op is op text, which we have not parsed yet. Divisible is divisible, right? And then true is true monkey. False is false monkey. And then throw new divide. And then just, yeah, that's fine. Yeah, throw new divide by 0. Okay, let's see if we parse the first one. 7998, op is times 19. Divisible is 23. True is 2, and false is 3. So that looks okay. Now we just need to parse the op text. So operator, let's see, op is op text sub 0. Let's see. If op is plus, else if, let's see, otherwise we know it's going to be multiply. All right, so if op text sub 2 on is equal to old, then let's see, we need a func of long to long operation. Operation is x plus x. Else operation is given x, it is x plus long parse op text 2. All right, and then we do the same thing down here, except your multiply and your multiply. All right, and then we say, actually leave that there. We're going to say we need monkeys. New list of monkey. All right, so we need a monkey. Come on. Var monkey is a new monkey. It's going to be items. It's going to be operation. It's going to be divisible test. It's going to be the true monkey. And it's going to be the false monkey. And then we go, let's see, 0, 1, 2, 3, 4, 5, 6, 7. So we say index plus equals 7. Items is a list of int. No, that should be a list of long. List of long parse. All right, yeah, list of long. Okay. The text shows basically just this, which is the items. Okay. So var round is 1. All right, let's make sure we do this. While round is less than or equal to 20 for rounds less than or equal to 20, double plus round. So the steps are, everybody runs an operation on their value, right? So we need to run a monkey. Give us a monkey. Right, so given a monkey, we do for each var item and items. Let's see, let's do this. Var current items. Items is monkey, let's see, monkey items to array. So we get a fresh copy, so the current items, right? And then we say monkey items clear. All right, so for every one of these, we do, let's see, new item is monkey.operation against the item, and then we divide by 3, right? And then test, we say if monkey dot, if new item mod monkey dot divisible test is 0, then we say monkeys sub monkey dot true monkey, right? Items add new item. Else this goes to the false monkey. False monkey. Okay, whatever. All right, so we run a monkey, we run every monkey, right? And then we say for index is 0, index is less than monkey's count, double plus index. We say run the monkey, monkeys of index. I think that's it. Right, and then we're gonna do same thing just so we can do console right line monkey index is this, which is monkey's index items. Select toString. Right, we're going to do a string join. All right. Let's make sure you get the logic right. On the single monkey's turn, it inspects and throws all the items it's holding one at a time in the order listed. Monkey 0 goes first. Okay, when a monkey throws an item, the item goes to the end of the monkey's recipient list. Let's see. Operation shows how the worry level changes. An operation like new equals old times 5 means worry level after the monkey inspected the item. Test shows how the monkey uses your worry level to decide where to throw the item next. Okay. After each monkey inspects an item, but before it tests your worry level, your relief that the monkey's inspection didn't damage the item causes the worry level to be divided by 3, rounded down. The monkeys take turns. Okay. Let's see. Monkey inspects 79, sees 1501. Monkey gets bored with the item. Worry level is divided by 3 to 500. 500 is not divisible by 23. Fine. Okay. So after one round. So let's run let's run one round and see what happens, right? Type argument cannot be inferred from usage. Monkeys idx.items.select. Oh yeah, toString. Input string ol plus x not in the correct format. What did I do wrong? That's very much the wrong thing. Op text. If op text 0. All right, so op text is 23, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, that's supposed to be 19. It's supposed to be 19. Items, so that's 18, that's 19, that's 21, 2, 3, 4, 5, 6, 7, 8, 9, and 30. Input string old plus 6 was not. N64 parse to list. Line 20. Index is 0. Okay, why is that index plus 1? Index starts at 0. Console right line index, let's see. Right? Console right line data at index. Data at index plus 1. So starting items, and then we've got 7 starting items. Okay, so I jumped too far ahead. This is supposed to go, oh right, because of course I eliminated all the blank lines already. Of course. Okay. Round is less than or equal to 1, double plus round. Okay, we didn't add monkeys. Monkeys add monkey. Input string d times 19 was not in the correct format. D times 19 was not in the right format. So operation, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. All right, so that was supposed to be 23. I second guessed myself incorrectly. All right. So is that what it's supposed to look like? 20, 23, 27, 26, 20, 80, 25, 167, 207, 401, 1046. So let's just print out the monkeys after 20. Right, so let's do 20. Let's print out the monkeys after 20 and see how we did. Okay. 10, 12, 14, 26, 34, 245, 93, 53, 199, 115. Okay. So the other thing we're supposed to do is we're also supposed to talk about inspection, right? So every inspection, so that's in run monkey. Monkey inspections, double plus. So we'll say public long inspections starts at 0. So we do double plus, and then we say top 2 is monkeys, order by monkey inspections, except we want to order by descending. take 2 to array, right? Return top 2 of 0 inspections times top 2 of 1 inspections. Let's make sure that that is correct. 106.05, that certainly sounds right. 106.05 for 20 rounds. All right, let's go get the real data. And run it, and run it. 99840. 99840, come on. 99840. Okay, part 2. You're worried you might not ever get your items back. So worried, in fact, that your relief for the monkey's inspection and damage time no longer causes your worry level to be divided by 3. Unfortunately, that relief was all it was keeping your worry levels from reaching ridiculous levels. You also need to find another way to keep your worry levels manageable. At this rate, you might be putting up with these monkeys for a very long time, possibly 10,000 rounds. With these new rules, you can still figure out the monkey business after 10,000 rounds using the example above. Two most active monkeys, blah, 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 multiply them together. Worry levels are no longer divided by 3 after each item is inspected. You need to find another way to keep your worry levels manageable. Start again. So I guess what they're saying is the number is going to be bigger than a long, but I guess we'll find out, right? Divide by 3, bool. Divide by 3. If divide by 3, then we're going to say new item divide by equals 3. So we divide by 3 here, and we don't divide by 3 here, and then we don't divide by 3 here. We got big numbers. My guess one is, though, we must have had some on overflow, 348099. Let's just go see. Yeah, we must have some overflow, obviously. 100,000. Oh, it's also we need 10,000 rounds. So let's do the old data. We forgot about that. So 10,000. 26. Well, apparently that's still doable. Let's see. No. Oh no. So we've definitely got overflow going on here. So yeah, that's what they were implying, which makes sense. So what is the easiest way for us to do this? There is like a big int class, I think. Let me do a little bit of let me go ahead and pop a browser up here. C# int bigger than 64-bit. All right, use big integer. Big integer. Okay, let's try that. Big integer. Big integer, big integer, big integer, big integer, big integer. All right, so what's left here is probably big integer parse, right? And then the operation is going to be big integer parse. And so we do plus and all right, this is going to be a big integer, big integer. So that's all okay. Big integer, big integer. Oh, let's see what happens. Takes a long time. Yeah, that's taking a long time. So let's say if round mod 100 is 0, console write dot console write line. Let's see how fast these hundreds are going. All right, so they basically stop. So this isn't a useful strategy either. Let's see. Yeah, go away for a minute. All right, input does not have to be there anymore. It's not that important. So level of monkey business after 10,000 rounds. Okay, so is there something we can discern about these things? These appear to all be primes. Is there something special about primes? Or do we only ever have to keep let me put all the big integers back to longs. Do we only ever have to keep, is this 13, 3, 19, 17, 11, 5, 7, 2? There's got to be something weird about the fact those are all primes. I mean, they don't usually send you on a wild goose chase like that, but let's try this. Console right line monkey. Let's see. Monkey top. Yeah, that's not going to help. Let's see. Well, maybe it'll help. Let's do top 2 sub 0 dot inspections times top 2 1 inspections equals result. All right. Return the results. All right, return 0. What did I miss? Oh, yeah. So 320, 312. This is the old data, right? 320 and 312. I think this is the old data. No, this is the new data. 105, 101. 105, 101. Hmm. So there's something with primes and the fact that we only add and multiply and we don't do anything else. Hmm. So obviously we know if we're going to add, let's see. We know if we're going to add, we could just take the mod and keep that. Right, because let's pick 7. Right, let's see if we can reason this out. Let's say 7. Let's say we add 7 and, or sorry, we're going to do mod of 7. That's our test. Let's start out with 3, right? And then we get, multiplied by 15. So x is 3 times 15 is 45, right? So then the mod 7 is going to be false. And if we're going to do this again, so then we have 45 times 15. Yeah, all right, I can't do that in my head. 45 times 15 is 675. Like, let's say you were going to be mod 7. So divide by 7, divide by 7. Huh. Yeah, there's got to be something that I don't understand about how to make this number stay smaller. Because we obviously we just can't let the number grow unbounded, right? And the problem is the test is always going to be different because the values get thrown around. So it's not like you can optimize knowing one operation over and over again. What's special about modulus of a prime number? Think about primes when you're looking at modulo. You can always divide anything by okay. Mathematics modulo prime number form a field. Okay, that's not even. Why modulo prime preferred over modulo composite? Encryption processing is okay. That is not going to be text that I understand. Why do we use modulo with a prime number? This means every multiplication maps to a different integer modulo of the primes. So does every addition. Prime moduli are advantageous because they give the most freedom when choosing the secondary multiplier and second. Okay, no. What is the modulus of a prime number? Recall, a prime number is a whole number greater than or equal to 2 whose only factors are 1 and itself. Right. Easier than normal. Modular arithmetic can be easier than normal arithmetic and more difficult. But when n is a prime number, then modular arithmetic keeps many of the nice properties we're used to with whole numbers. Recall that a prime number is a whole number, blah, 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 sure. Inverses modulo prime. When n is a prime number, then it is valid to divide any non-zero number, that is... Oh, this is an interesting thought that I just had. What if we store factors? Right, so instead of storing a whole number, we store the factors of that number. Because we know the modulo is always going to be a prime, right? Then that means we know that we can always just keep a list of all, because factors are all primes themselves, right? All right, so let's see, C# get factors of a number. Loop from 1 to the square root of the number. If the number mod I is 0, add I. Except we would just start with 2, right? So then adding a value, well, the problem is adding a value creates new factors. But I think if we just have, if the number that we keep is just the factors, is there, yeah, because the operations definitely include addition. So squaring, adding, multiplying. Multiplying just adds the factor into the factors list. Well, adds all the factors of the multiplier into the list. All right, so let's walk through that idea. So let's say we have the number. Let's say we have the number. I don't know. Let's do 65. Sure, right? So the factors here are, we know 5. So 5 times 15, 5 times 13 is 65. Actually, that's it. 5 times 13 is 65. Right, so if we multiply, then we just add the factors of the multiplier. If we add, then we need the number, need the base number, add, and then refactor. Is that good enough? All right, so if 65 is 5 times 13, let's add 7. Okay, so we have 65 plus 7 is 72. All right, so then that gives us 9, which is 3 times 3, 8, which is 2 times 2 times 2, which if we only care about factors, then we have factors of 2 and 3, right? That's where we end up. Now, let's say we have 100 and, let's see. Let's say we have 65 times 5, so that's 325, right? So we have 325, which is 5 times 5 times 13, which gives us 5 and 13 again, right? And now we add 7. So then we would say 325 plus 7 is 332. So 332 would be 2, gives us 161. Is 161 a prime? I swear I'm picking terrible numbers. Is 161 prime? No, okay. 1, 7, 23. So 7 and 23. So 7 and 23 times 7 times 23 times 7 times 23. So that gives us 2, 7, and 23. So that's not even close to being correct. Like if we were just doing multiplication, this would be easy to do. So starting with those same factors. Yeah. I feel like the factors is potentially a correct direction to go. I just don't know how to use it. Let's see. C#, very fast, arbitrarily large integers. Bit counting arbitrarily large positive numbers in C#. Bit counting arbitrarily large positive. Manipulation bit counting, and you test an arbitrarily large and it contains at most 2 bits. That's actually not the problem I have. C# solution for big numbers. Looking for a solution to big numbers. My game will have big numbers, 799, and will float, and it will be float like numbers with precision of 1 place after the comma. What library? Decimal, double, but a much shorter. Yeah. So I don't want anything that's lossy like double. If you want to work with incredibly large numbers, look here. Mega integer string calculator. Calculator for very long numbers. Max length of string. Integer style math. Okay. Okay. Wow. So basically, this is just using strings. Big integer. This big integer type is immutable, and because it has no upper or lower bounds, an out-of-memory exception can be thrown for any operation that causes big integer to grow too large. I feel like I'm solving the wrong problem. That's really, I feel like I'm solving the wrong problem. What is special about this data? No, I really don't have any idea. I thought the factors thing might be interesting. The problem is, well, the factors thing would make the multiplication easier. But when it came to addition, we'd basically have to remultiply all the factors together. And that just doesn't seem like, how is C# big integer implemented? Recommend you take a look at alternatives. A GNU multi-precision library. You can also take a look at this implementation of big int. GNU multi-precision library. Arbitrary precision arithmetic, operating on signed integers, rational numbers, blah, 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 blah. Question is, Blah, blah, blah. I don't know that this is necessarily going to be helpful. Specialized for cryptography at the neglect of memory considerations. Implemented as a constant linked array, memory is quickly exhausted, performance degraded when the length is even moderately high. But awkward to use, reference type, no operators, and also requires distributing the J-sharp runtime. Linked list of bytes in base 10 has memory consumption performance is not optimal. Yes, that doesn't help me. There's a big integer in bouncy castle. Okay. Portable bouncy castle nougat package. Portable bouncy castle nougat package. Portable bouncy castle. I mean, can try that again. Okay. Item group, package reference, include version. What is your version? 190. 190. So we don't have operator can't be big integer to big integer. That's interesting, really? All right, inspections can continue to be long. You can continue to be long. Well, actually, you shouldn't be. You should be, though. Right, we believe that that is correct. That should be that. So here we have, all right, so let's go look at big integer and see what operations exist on big integer. Oh, you have a bunch of primes. I like that. So your operations are what? So we have square, for example. Okay. So what that means is these operations that we are doing here is going to be x dot add big integer parse text 2 dot, right? So there isn't a parse from, wow, there's no parse. What are our, can you just take a string? Oh, you can just take a string. That's fine then. New big integer, right? And then this is going to be x add. Except what did I do here? This is old. X dot add to x. That was my bad. Why do you suddenly work? Yeah, there's no way you just suddenly work. Right. So your square multiply. Okay. Are you going to work now? So we still have things that are broken. New item equals new item dot divide 3. Big integer dot 3. Let's see, new item dot modulus mod. You're going to return a big integer. So we're going to say if equal to big integer dot 0. Do you build? Sure. This is line 21. X is a string. Oh, you probably just need to be trimmed. Debug. Okay, we'll debug this time so that we can do a break. Find out where we're stuck. Debug, break all. Okay. What round are we on? 241 out of 10,000. Yeah, this isn't going to work either. It's just too slow. I don't think I have an answer. The last thing I could think to Google would be how to store arbitrarily large numbers when you only care about modulus with a prime. Finding modulo for large numbers. I'm not going to watch that 11-minute YouTube video. Look at the modulo of a very large number. There has to be something about the fact that the modulo operations are all prime. Why do we use prime numbers in modulos? Primes are used because you have a good chance of obtaining a unique value for typical hash functions. How to expect to be. That's not helpful. Let's see, modulus of large numbers. So you want to calculate, now even see if first reduce A mod M. That means find number A. And repeat the loop. Yeah, that's might be helpful to someone, but just not me. That is not. Let's see. Big integer, try big integer. Super fast modulus with prime. So we were here, modulo prime number, okay. Inverses modulo prime. When n is a prime number, it is valid to divide any non-zero. Okay. Thus dividing a is the same as multiplying by u. Division of a is given by the rule. Mod 7, we have 1 over 1 is 1, 1 over 2 is 4, 1 over 3 is 5, 1 over 4 is 2. What? Oh, this is the mods. No, I don't understand that either. As a prime number, then modular arithmetic keeps many of the nice properties we're used to with whole numbers. Yeah, that is not what we wanted. For reduction modulo of prime. If prime p is bonds, any fast modulo is prime. Integer n, choose some integer a, coprime to n, calculate blah blah blah. Nope. Nope. I'm out of ideas, and everything that I search for is confusing me more than helping me. So I'm gonna end the stream because I honestly don't know how to solve this problem. I don't know if I'm gonna get this started today or not. I'm gonna have to think about it a little bit, I guess. Well, one way or another, I'll see you tomorrow.